Hi, I thought I'd make a video to help explain some of the questions I was asking you last night and also just some of this topic we've been covering, the one sample t-test. First, let's start by looking at this. It says that a researcher is interested in whether the mean IQ of the population of all college students in the US equals 100. The researcher wants to know if he or she added up all of these IQs and divided by this number, would the answer come out to 100? There's two competing possibilities. Either it is 100 or it isn't 100. One of those has to be true. The researcher can't record the IQs of all of these college students, so the researcher has to depend on a sample of the population to make a conclusion about whether the population mean appears to be 100 or not 100. The researcher is going to take one sample of 3 people, in this case, add up those 3 IQs and divide by 3 to get a sample mean. And based on that sample mean of the IQs of the 3 people, the researcher is going to make a conclusion about whether the mean of all college students in the US appears to equal 100 or not equal 100. So let's talk about how that would be done. We have, well, I made this so that there would be some possible outcomes down here. These aren't the only possible samples that might be found. They're just 5 different possible data sets that I decided to work with. And I know that 3 people is a very small sample size, but I use that sample size just to make my point about these t-scores that I'm going to calculate. I know that these data sets right here probably look too simple, but because they're all 2 apart, but I did that just so I can make the concept more clear. Let's actually calculate the t-score of each sample, and then let's talk about what those t-scores actually mean. But before we calculate the t-scores, I wanted to make one important point. The null hypothesis says that the population mean is 100, and the alternative says that the population mean is not 100. Let's look at this sample here. This is a possible sample that the researcher might find. And if the researcher ended up recording these 3 numbers, the mean of the researcher sample would be 100, because when you add these 3 numbers and divide by 3, you get 100. If the researcher gets this data set right here, that doesn't mean that the null hypothesis is true. Just because this number says 100, that doesn't mean the null hypothesis is true. The null hypothesis is only true if the mean of all of these college students in the population equals 100. We talked about how the mean of a sample is not necessarily the same as the mean of the entire population. Actually, it's almost always not the same. So just because the mean of your sample is 100 doesn't mean that the mean of the entire population is 100. If the sample mean is 100, the population mean could be some other number. And the null hypothesis is only true if the population mean equals 100 in this case. In a one sample t-test, the null hypothesis says that the population mean, the actual population mean, equals the hypothetical number that the researcher is testing for the population mean. Remember I said the null is mu, the actual population mean, equals mu0, which is the hypothetical value that the population mean might or might not equal. In other words, the null is true if the actual population mean equals whatever number the researcher is testing for the population mean. In this case, the researcher is testing 100, which means mu0 is 100. So the null just becomes mu equals 100. And the alternative is the opposite of that. So back to this point here, if your sample mean turns out to be 100, and the actual unknown population mean is actually 99, then the alternative is true because the population mean is not 100. Even if your sample mean is 100, if the actual population mean is 99, then the alternative is true because the population mean is not 100. If your sample mean is 100 and the unknown population mean is also 100, then that's when the null is true. And if your sample mean turns out to be 104, if you get this data set, the null might still be true, because if the mean of your recruited sample is 104, and the unknown population mean up here is actually 100, then the null is true, even though your sample mean was not 100. So main point is that the null says that the population mean equals a certain number, not that the sample mean equals a certain number. So now let's calculate these t-scores. The formula for t is, I'll put it over here, x bar equals, I'm sorry, t equals x bar, the sample mean, minus mu0, the hypothetical value that the population mean might or might not equal, over the sample standard deviation divided by the square root of n, the sample size. Let's do this for this sample right here, sample 3. 100, sample mean of 100, minus the hypothetical value of the population mean. In other words, the number that the researcher thinks the population mean could equal, over sample standard deviation of the sample, which is 2 here, and divide that by the square root of n. Right here, n is 3 because it's a sample size of 3. What ends up happening in this case is we have 0 on top over 2 divided by the square root of 3, which actually has to equal 0, because regardless of what this equals on the bottom, when you divide 0 by something, you have to get 0. So here, t is 0. Let's do this one right here. Sample mean is 104, minus the researcher is still testing whether the population mean is 100. We're just looking at a different possible outcome. So the hypothetical population mean is still 100. The sample standard deviation is still 2. And we divide that by the square root of 3. Let's see what this comes out to. We found the square root of 3. Let's divide 2 by the square root of 3. We get 1.73. So what we have is 104 minus 100 over 1.73. we subtract on top, it becomes 4 over 1.73. And what do we get when we divide 4 by 1.73? 2.31. That's what this t-score equals. Let's do this one right here. The only thing that's going to change is that the sample mean of 104 is now going to be a sample mean of 106. We know that 2 divided by the square root of 3 is 1.73. Six over 1.73 is 3.47 about. I could also calculate these other two t-scores with you, but they're just going to come out to the negative versions of these two numbers because this one will be 98 minus 100 on top, which will be a negative 2. Wait, actually they won't come out exactly the same because this is 4 and then this is 2. So maybe I'll make them the same. I'll make them the same distance from 100. Now this one actually will be negative 4 on top. It would just be negative 4 over 1.73. And this one over here would just end up being negative 6 over 1.73, which would mean that these t-scores would just be the opposites. Okay, now that that's finished, let's find out what the critical t-scores are. Go to our t-table. You have to go to one less than our sample size, which is a df of 2. We're looking for both the positive and the negative critical values, which means we use two tails. You go to 0.05. You almost always go to 0.05 for the critical value. And then we get 4.303, which means our positive critical value is 4.303. And our negative critical value is negative 4.303. Which means actually none of these outcomes reached the rejection area because none of the t-scores reached the positive critical value or the negative critical value. I would like to be able to add an outcome that does reach the critical value. It throws off the numbering, but we'll just ignore the numbering. We'll do 106, 108, and 110. Sample mean is 108. I'm giving you the standard deviation. I actually know that t will be 4.3, which isn't enough. Sample mean is 110. If you add them and divide by 3, you get 110. This one is 5.46. This one down here is, if we add another one down here at 88, if we start at 88, and then this one would have a t-score of the opposite. You could calculate the t-score to make sure that I'm correct if you want to. Oh, sorry. move the critical value just so it looks nicer, so it fits between them. So actually we do have an outcome in the negative rejection region down here below the negative critical value, and we have an outcome in the positive rejection region up here. Now what we'll do is we'll calculate the p-values of each of these t-scores, and we'll see that as t moves further from 0, p drops, gets lower, and once it passes the critical value on either side, p is less than 0.05. Let's go to our p-value calculator. This is 1 less than the sample size, so we'll have to enter 2. We'll start with 2.31. .1471. 'Naturally, these p-values will, if t is 0, p has to be 1. Going down in this direction, the p-values will be the same because the t-scores are just the opposites. Okay, we can see that the p-values beyond the critical values have a p. We can see that the t-scores beyond the critical values have p-values less than 0.05. The critical values themselves would each have a p-value of exactly 0.05. But now let's think about what I actually wanted to get into. we have this sample of 3 people that we selected, and we're saying that we're going to get one of these data sets. I mean, we're not definitely going to get one of these data sets, but these are some hypothetical data sets that could be found with 3 people. And once we get our sample of 3 people, we know what the sample mean equals because we can actually calculate it. What we don't know is what the mean of the population was. We don't know what the mean of the population that the sample came from equals. Up here, the mean is unknown. And as a researcher, I care if it equals 100 or not 100. So I care if the mean of the big box of these people equals 100 or not 100. The mean of the sample is something else. That's what we actually see down here. That's not the same thing. So there's 3 possibilities that could be true. Either my sample is coming from a population that does have a mean of 100, and my hypothetical value is correct. The population mean does equal the hypothetical value I'm testing. If this is the case, then, and if my sample is coming from this population, then the null is true. But the population mean could be lower than 100, which is one version of the alternative hypothesis. And the population mean could be above 100, which is also the alternative. So down here, the population mean could be something like 98 or 97. Up here, it could be something like 102 or 103. The main point is that this is the situation in which the population mean is under 100, and up here is a situation in which it's above 100. So the question is, which population did the sample actually come from? 1, 2, or 3? Well, we can't see the population, so we have to rely on our sample to make the decision. And remember that we're only selecting a sample from one population. These are just 3 hypothetical populations. It's sort of like a parallel universe. You just don't know if the population mean is under 100, equal to 100, or above 100. But either of these could be true. But remember, the sample is just coming from one population. Now, let's see what outcome would be expected in each of these situations. If the population mean is under 100, if it's something like 95, let's put 95 as a hypothetical number, we would expect for the sample mean to come out somewhere near this number, if this is the actual population mean. So we would be expecting outcomes down here somewhere. These types of outcomes would be likely because these are sample means that are near this number. If the population mean is 95, you expect a sample mean somewhere near 95, such as a sample mean of 94 or a sample mean of 96. So if the population mean is under 100, we would expect a sample mean somewhere down here at the left end. And because of that, we would also expect a more highly negative t-score down here somewhere. What if the population mean is something higher, like 105? Well, if the population mean is 105, you expect a sample mean somewhere near 105, which would mean that these outcomes up here toward the right would be more likely in that situation, and you would expect a more highly positive t-score. But what if the null is true and the population mean really is 100? What if it really does equal what we're testing? Well, then the sample mean should be somewhere near 100. So if this situation is true, if the null is true, you expect a sample mean somewhere around 100. If the population mean is 100, you expect the sample mean somewhere near 100, which is somewhere in the center area. And because of that, well, notice how if the sample mean is 100, you get a t-score of 0, and sample means near 100, like 99 or 101, have t-scores near 0. So if the population mean is 100, you expect a sample mean near 100, and you expect a t-score near 0. So that's what's likely in each of these situations. So it turns out that in this situation here, if the population mean is 100, I said you expect a sample mean near 100, and because of that, you expect a t-score near 0 because sample means near this center outcome do have t-scores near 0. For example, if the sample mean was 101, the t would be a little bit above 0. If the sample mean was 99, it would be a little bit below 0. So if the population mean is 100, you expect a sample mean somewhere near 100 and a t-score, and because of that, you expect a t-score near 0. In this situation here, t-scores further below 0 are less likely, because if the population mean is 100, you're less and less likely to get these sample means further below 100 that would give you those highly negative t-scores down here. And if the population mean is 100, you're less and less likely to get these sample means further above 100 that would give you these more highly positive t-scores. So if this center outcome is true, if the population mean is 100, outcomes out here are less likely, the highly negative t-scores. The outcomes out here are less likely, the highly positive t-scores. And it turns out that if in this middle situation, you can actually calculate probabilities. You can actually find out that if the population mean is 100 and the null is true, you can actually look at the probability of getting different outcomes in that situation. Well, it turns out that if the null is true and our population mean is 100, if the center outcome is true, then we have a 0.1471 chance of getting somewhere in this red area, starting at that t-score that has that p-value, and also beyond the opposite of the t-score, which has that same p-value. If the null is true, we have a 0.1471 chance of getting a sample with a t-score in either of these two red areas. If the null is true, and our sample did come from this population right here with a mean of 100, we have a 0.074 chance of getting a t-score starting here and going out, starting at that t-score with that p-value and going out, and also beyond the opposite t-score that has the same p-value. So if the population mean does equal what we're testing, and we're taking a sample from that population in this middle situation, I explained that t-scores further to the right are less likely, and sample means further to the left are also less likely. But this is actually showing exactly how unlikely they're getting. In this middle situation, in which the null is true, the two red areas, either red area has a 0.1471 chance of being reached. Either of the two green areas has a point, 0.074 chance of being reached. So notice how as the t-score is getting further out from the center, the p-value is dropping. Because since in the null situation, the outcomes further from center are getting less likely, that's why the p-value is dropping. Let's look at this last one out here. This outcome with a t-score of 5.46 has a p-value of 0.0319. So does the opposite t-score. So what does this mean? It means that if the null hypothesis is true and the population mean is 100, we have a 0.0319 probability of reaching either of the two blue areas, starting at that t-score and starting at the opposite t-score. That's why they both have 0.0319. So 0.0319 isn't a very high chance of being reached. I mean, 0.0319 is a pretty low probability. So it turns out that these two blue areas have a pretty low chance of being reached if this center outcome is reality, if this really is the case. Let's think about why that would be true. If you take a sample from this population, why is it so unlikely to reach one of these two blue areas? Well, because if the population mean is 100, you have to get a sample mean pretty far above 100 to reach this blue area out here, and we know that if the population mean is 100, you're not likely to get a sample mean far above 100 out here. And if the population mean is 100, in order to get a sample mean far down here, well, if the population mean is 100, you would have to get a sample mean far below that number to reach this blue area. So if this middle situation is the case, if that's the population mean, then to get to this blue area, you would have to get a sample mean high above the population mean of 100. And down here in this blue area, you would have to get a sample mean pretty far below that population mean of 100. And we know that we're not likely to, if it's a random sample, we're not likely to highly overestimate or highly underestimate. So if that's the population mean, if this is true, to get to either of these two blue areas, you would have to either highly overestimate the population mean with this sample mean, or highly underestimate it with this sample mean down here. You would have to do one of those two things to get to these blue areas. That's why these two blue areas only have a 0.0319 chance of being reached in the null situation with this up here. Now, if I get the sample mean of 110, I know that that's unlikely if the null is true and the population mean is 100, which is why I would reject the null hypothesis in this rejection region out here, beyond the critical value. But if I get out here, what specific conclusion would I make? Well, if the population mean is somewhere above 100, like 105, then this outcome, this high sample mean, becomes more likely. If the population mean is high, the sample mean is more likely to be high also. So this outcome out here, sample mean of 110, with this t-score would be unlikely in the middle situation, but more likely in the right situation, which is why if you make it to the positive rejection region, you go with this conclusion that the population mean appears to be above the number you're testing, which is 100 in this case. If we get this sample mean of 90 with this highly negative t-score, we know that if the population mean is equal to 100, if the null is true, we're unlikely to get this sample mean down at 90 with this t-score, because if the population mean is 100, it looks like you're unlikely to get a sample mean way down at 90 with this t-score down here. So it's unlikely in this situation. So this is rejected again. But if the population mean is actually something lower than that number, if it's like 95, then a sample mean down here at 90 would be at least more likely, because if the population mean is 95, a sample mean of 90 would be at least more expected, because 95 and 90 are more close compared to 190. So if you get this outcome down here, this low sample mean, it's unlikely in the middle situation, but it's at least more likely in this situation to the left, in which the population mean is less than 100. So if the sample mean is low, if it turns out low, then it suggests that the population mean is also low, because the sample mean and population mean should be close together. So if you get this sample mean down here at 90, you reject 100 as the population mean, and you conclude that the population mean appears to be lower than 100 and somewhere closer to the mean of the sample that you found, which was 90 down here. So what I've said is, if you get an outcome up here, if the sample mean is too high, then conclude that the population mean is higher than the hypothetical number. If the sample mean is too low, you also reject the middle outcome, and you conclude that the population mean is lower. So if the sample mean is too high, conclude that the population mean is higher. If the sample mean is too low, conclude that the population mean is lower. And I said that you reject the null hypothesis when the outcome is an outcome that would be unlikely in the situation of the null being true. In our study, this is the situation of the null being true. And in that situation, and I told you that in that situation, these outcomes far to the right and far to the left are unlikely. The outcomes in the two rejection regions are highly unlikely in that situation, which is why the outcomes in those two rejection regions lead to the rejection of this outcome. So if you get an outcome way to the right, it's unlikely if the null was true, so the null is rejected. If you get an outcome far to the left, it's unlikely if the null was true, so you reject it. But in other words, a population with a mean of 100 is unlikely to give you a sample way out here with this type of a sample mean, and a population with a mean of 100 is also unlikely to give you a sample mean. It's unlikely to give you a sample with a mean way down here, which is why if you get a sample way up here or way down here, you reject the middle situation. And you make opposite conclusions at the two ends.